this podcast we're going to take a look at doing some practice with determining the equilibrium concentrations of weak bases and strong bases. Okay, so in the first problem we're asked what is the hydroxide concentration in a 0.15 molar ammonia solution, so that's a weak base, and the Kb is given to us and the balanced equation is given to us. So what we can start with is we need the ice table because this is a weak base. And if I start with 0.15 molar of ammonia, I start with no products. I set up my rice table and I end up with the equilibrium expression of x squared over 0.15 minus x. I'm going to assume that x is insignificant and rearrange the equation. I end up with 1.8 times 10 to the minus 5 equals x squared over 0.15. I multiply both sides by 0.15 and I end up with 2.7 times 10 to the minus 6. If I take the square root of both sides, I end up with a hydroxide concentration of 0.00164. Whoops. Okay, so now the same problem is asking for us to calculate the pH. And I have the wrong slide up, but I think you have the right slide there. So if my hydroxide is 0.00164, then I know my pOH is the negative log of that, and that comes out to be 2.785. And I'm going to make the assumption that pH is plus pOH is equal to 14, assuming we get 25 degrees C. So I can subtract my pOH from my 14, and I get a pH of 11.21. Okay, and that makes sense because it's a base. It's a weak base, so it's not going to be as high as 13 or 14. Okay, so let's take a look at another one. Here we want to identify each of the following as a strong or weak acid or base. So one of the things you have to do in this course is memorize strong acids and strong bases. Okay, so from group 1, I have 3 hydroxides that are strong bases, and they're at the top. It's lithium, sodium, and potassium. And then from group 2, I have 3 bases that are, 3 metals that form hydroxides that are strong bases. Magnesium hydroxide doesn't, because it turns out it's not that soluble, so it won't completely ionize. So it's calcium, strontium, and barium. So there's 6 of them, and you've got to have those memorized. So if those are the strong, then potassium and barium hydroxides are going to be strong, and the other 2 are going to be weak. Okay, so here's a table that's actually quite a bit of work to figure all this out. So it's good practice for you, and I encourage you to do it. The first thing you need to do in any of these is identify whether you have stuff that's strong or weak. So there's your identifications. And here's the answers along with how you do each conversion. So good practice if you think you need it. I'm going to take a look at determining the pH of 3 different bases. All have the same molarity, but they're different types, and we'll take a look at what we do differently for each of those. So be careful. Whenever you're told to find the pH of something, the first thing you have to determine is whether or not you're given an acid or a base. So obviously we have a base here because it's got the hydroxide. And then we have to determine whether it's strong or weak. So potassium hydroxide is strong. So when we have a strong base, we know that it's going to completely ionize, which means that if I start with 0.25 molar of this, I'm going to end up with 0.25 molar of the hydroxide, right? So all I need to do to get the pOH is say the negative of the log of the OH minus, which is going to be the negative of the log of 0.250 molar, and that's going to give me a pOH of 0.602, so my pH is simply going to be 14 minus the pOH, which is 6.602, so that's going to be 13.398. And that number makes sense. First of all, there's 3 sig figs in my concentration, so there's going to be 3 in my mantissa with my pH. This number makes sense because I have a strong base, so the pH is going to be very, very high, close to 14. Okay. So here we have barium hydroxide, same concentration. So It is a base, and it is a strong base, but the thing that's different here is I have two hydroxides. So what happens if I have barium hydroxide, and it ionizes, which it will completely in water, right? That's the definition of a base. For every one of these, 0.25 molar of this, I'm going to end up with twice as much of this, right? Because I get two hydroxides. So now when I do my POH, I have to say it's the negative of the log of the 0.500 molar, which is going to be 0.301. So my pH is going to be 14 minus my POH, which is 0.301. So that's going to be 13.698. And that makes sense. Again, very high pH, even higher than it was with potassium hydroxide, because for every one molar of the base, I get twice as many hydroxide. Alright, so strongs are easy, weaks just take some work, right? So here I'm given ammonia. I have to recognize that that's a base, and it's a weak base, and it's giving me a Kb, which is pretty small. So the first thing I have to think about is where do the hydroxides come from? So if I take my ammonia and I put it in water, what's going to happen is I'm going to end up with ammonium ion and hydroxide. And it won't completely ionize, it's a two-headed arrow, so if I start with 0.250 molar of this, and I start with none of these, this is going to lose X, this will gain X, this will gain X. So my ice table, my equilibrium is going to be 0.250 minus X, X, and X. So what I know is my Kb, which in this case is 1.8 times 10 to the minus 5, is equal to my products, which would be X squared, over my reactant, which is 0.250 minus X. Now, because my Kb is so small, I know that my X is going to be tiny, so I'm going to use my simplifying assumption and get rid of that. So if I cross multiply 1.8 times 10 to the minus 5 times 0.25, I'm going to end up with, let me see, 4.5 times 10 to the minus 6 is equal to X squared. If I take the square root of both sides, I'm going to end up with X equals 0.00212. And that's my hydroxide concentration, right? So my POH is going to be the negative of the log of 0.00212, and that will be 2.673. So my pH is going to be 14 minus 2.673, or 11.32. I want 2 sig figs in my mantissa. Actually, I should have 3. So I'm not sure what that third one is because I did this before I don't have my calculator now. Okay, so we're going to stop it right there. And it makes sense that this number's smaller, right? Okay.